Today we talk about electric charge. Some experimental facts. If you rub two glass rods with wool, they will repel each other. If you rub them with silk, they will repel each other. But if you rub one glass rod with silk and another with wool, they will attract each other. And if you put the wool rod in contact with the silk rod, it won't respond to any other such rods. These are weird facts that have been discovered more or less over thousands of years, but solidified in the early 1700s. The model that leads us to is saying that rubbing the rod with wool or with silk transfers something called charge to it, but there are at least two different types. The two charge types act like positive and negative numbers. Rubbing the rod twice as much with wool produces twice the attraction because, for instance, plus another plus, maybe that's badly done, plus charge plus some other charge yields two charges, but also negative plus some other negative also yields two negatives, but most importantly for all of this, plus added to a negative yields nothing. All right, adding the two charges together makes the rod neutral because minus 1 plus 1 is 0. Very important to understand, it's not clear observationally which charge is positive. In fact, it's very arbitrary. There are no experiments you can do that tells you which of those is the positive charge and which is negative, only that one is positive and one is negative. Ben Franklin randomly chose that a rod rubbed with silk acquires the positive type of charge. We will have reason to believe wish he had done the other. Our modern understanding is that matter is made of atoms, which in turn are made of nuclei surrounded by negative electrons. The nucleus itself, being positive, is made of positive protons and neutral neutrons. The charge on the proton is equal to the charge of the electron, except opposite in sign. All protons have the same charge, and all electrons have the same charge, which is equal to the proton charge, but negative. We call the fundamental unit of charge E. Yeah, that's not a great choice because, of course, we'll also have exponential stuff going on, but we're stuck with it. And the charge on a proton, therefore, would be E+, and the charge on an electron would be E-, which is minus E+, although we usually write the proton as P, not as E+. That's because they have wildly different masses, so you don't want to confuse the two. And it turns out in fundamental physics, will turn out there is something which is like the electron but positive, so we use the E+ symbol when we're talking about particles for that. Each atom is neutral and has equal numbers of protons and electrons. If there's not an equal number of them, then we have an ion, not an atom. This is something that chemists really focus on, and physicists are, as is our wont, a little bit more sloppy than that. The units of charge were settled long before the atomic nature of matter was established, so the unit of charge was set by considering something called electric current and had no idea how many electrons or protons would be involved. We won't get to current for a while, so we won't see how this works, but 1 amp of current is a real-world human scale kind of thing, and because of that, the coulomb ends up being this obscenely large amount of charge, like crazy huge. The unit of charge in SI is called the coulomb. It's symbolized by capital C. Turns out it takes about 6.25 times 10 to the 18 electrons to have 1 coulomb of charge. That is to say, let's see if I get this right, 625, and then we need, 16 other zeros. So 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. About that many electrons to get 1 coulomb of charge. Crazy large. Much more importantly, from the viewpoint of test taking, one fundamental electric charge is 1.6 times 10 to the minus 19 coulombs. And that's a number you're going to use a lot. So it's on your equation sheet, but you'll probably end up committing it to memory. The coulomb is a huge amount of charge. It's crazy large. It's virtually impossible to assemble that much charge on any kind of human scale object, just because that amount of charge would push away from each other. The object needs to be huge to reduce that repulsion to manageable levels. Nonetheless, for examples that we'll use, we'll often pretend that we can have something like plus 1 coulomb or minus 4 coulombs or whatever. In other words, we'll often take huge numbers just to make it easy to talk about. Textbooks are usually a little better about this, to be fairer than I am, and they will often just talk about having like 6 microcoulomb. But then you gotta carry around the extra micro, and it's a little annoying. All right, materials can be loosely divided into conductors and insulators. Conductors have the electrons in them relatively easily move, and so they can jump from nucleus to nucleus, while insulators have electrons tightly bound to a particular nucleus. As with most categories that humans make, nature does not really respect this division. There are things that are weak conductors that are almost insulators. There are things that are weak insulators and are almost conductors. And there's a third class of thing called the semiconductor, which we will talk about very briefly later, but we'll ignore for this discussion. In an insulator, the electrons cannot move freely. That's what makes an insulator. Rubbing such a material can deposit a few extra electrons on the surface, or even pull a few electrons off the surface, but it creates a patch of charge that is itself immobile and relatively small. In a conductor, most especially a metal, the outermost or valence electrons are so loosely bound they can move from atom to atom. They create what's called the electron sea, in which sit islands of positive iron core. In quantum mechanical sense, all of the nuclei are sharing those valence electrons, so they can move easily from one to the other. In fact, little bits of them basically have, at any given time, been at all different places. Because the electrons are free to move, an isolated conductor will rapidly reach a state of equilibrium where mutual repulsions keep the electrons in check. It's a little weird to say because they move, they don't. But what we really mean is that on a very fast time scale, they get to where those forces cancel out, because if there's any imbalance, they can move in response to it. This state is called electrostatic equilibrium because the charges no longer move, even though they could, in principle, do so. All right, when a charged object, such as an insulator that has been rubbed with wood or silk, is brought into contact with the conductor, the excess charge will flow. So here we have excess negative charge, and we put it in contact with this conductor that has neutral charge. Of course, it's made of atoms, so it has pluses and minuses in it, but they're basically all neutralized and canceled out. And the excess electrons here will flow onto the metal, and then their mutual repulsion will move them to the corners, which is why they're shown as far as possible. This means the sphere has picked up a net negative charge. If, on the other hand, we bring in positive charges and touch it to a sphere that is originally neutral, the positives are not free to move, remember. These positives were made because somehow we stripped electrons off the rod. Instead, what happens is there are electrons on the sphere, along with their own little positives, and they are attracted, and they flow off of the sphere onto the stick, where they neutralize the given stuff, so we're back to being neutral. But that leaves behind their positive nuclei, and again, electrons will move around in such a way so that the positives have gotten as far from each other as possible. A useful device that shows the presence of charge is something called the electroscope, meaning a thing that sees electricity. It doesn't do either of those things, but that's what we call it. It's made of a metal sphere connected to a metal post that is then connected to very thin hanging gold leaves. For some reason, physicists like precious metals and rare stones. So gold is very famous with it a lot. We usually have it inside something else, often a glass box, so you can both see them but isolate the gold leaves, especially from the humidity in the air, which would make charge bleed off pretty easily. And then if there's charge on this whole system, these two leaves will have the same charge and they'll repel. If I bring charge in, say some positive charge, the mutual repulsion of the positive charge forces some of them down here. Some go on the left leaf, some go on the right leaf, and again, their mutual repulsion pushes them aside. It's why they need to be thin and light, so that they can counteract their own gravitational force. How does it work? Well, we bring in, say, some electrons. Negative charges are moved from the negatively charged rod onto the spherical conductor, onto the sphere, very fast, probably in something like order of a microsecond, maybe less. The electrons spread out as much as possible, and then down here they force the leaves open. What if it had been a positive rod? You'd see exactly the same thing. In this case, electrons would flow off of the sphere onto the rod. That would leave some electrons down here would then be attracted to the isolated plus charges up here, leaving positive charges on both leaves, which again would repel. You might notice that in both cases, although we talk about the electrons moving because that's physically what happens in metals, we would have been fine if we pretended that positive charges move. And until we do magnetism, you really can't distinguish the motion of a positive charge from in one direction from a negative flow in the other direction. All right. An electroscope will respond when a charged rod is brought near, even if the rod doesn't charge the sphere. And what's happening then? Well, there's no contact, so it's not that charge is flowing onto the leaves, at least not from the charged rod. For instance, if we bring in a positive rod, when we bring in a positive rod, the positive charges here will take, remember these are all positive, negative charges in the metal, and they'll attract some negatives. And they'll shift them over a little bit. And that will shift some other guys over a little bit to fill in that gap, and so on and so on. And the net effect will be there'll be a wall of negative charge here and a wall of positive charge here. It's a very small shift. It might be on the order of an atom or even smaller, but it does create an imbalance. This is called polarization. We say the rod polarizes the metal. It's very easy to see in the case of a conductor where charge can actually flow to get as close as possible to that positive rod. What if it had been opposite time? Well, here we can see what's going on here again, that we're getting some force upward. Right? These positives, they pull the negatives up, they push the positives down. On the other hand, the negatives are much closer, and we'll find out in our next section that the force is strongly dependent on distance, and therefore this repulsion is weaker than this attraction, so there's a minute upward attraction. Even insulators can be polarized. Now the electrons don't bulk move across it, but instead they shift slightly, and the nuclei shift slightly the other way. It makes their atomic shells look less spherical and more egg-like. And we create what's called an electric dipole. All right, we've taken the neutral object, it remains neutral, but we've given it an orientation in space according to that attraction. All right, electroscope is positively charged by touching with a glass rod. The electroscope leaves spread apart, so we have something like this, where we know that there are positives here and positives here. Looks a little bit like a stick figure. The glass rod is removed, but there was actual charge transfer onto the electroscope. Then we bring in a negatively charged rod. So there are negatives here, but it doesn't touch. So we don't transfer the negatives onto the electroscope. We just bring it close, this so-called induced charge. What happens to the leaves? Well, remember that inside, let's do a little X-ray of our electroscope. Oops. There would have been positives and negatives. These negatives repel those negatives, and they flow down. Right, they flow down and onto the leaves, where they neutralize some of the positives, and so therefore what we end up with is only, say, one positive on each thing. So we would get less separation.